I'm going to talk about testing, and just to get us started, I'm going to show an example of a test, and I'm going to test my favorite function for examples. Oh, the reverse function for lists. So here is a simple test for reverse. We could all write this. Just a standard kind of unit test. Everybody in this room has written thousands of them in their lifetime. So we just call the function that we want to test. We give it a sample argument. We predict the expected result, and then we compare the two. And that triple equals, that's an operation from Haskell QuickCheck that you can think of it as assert equals. It's going to display an error message if the test fails. So, very simple, but this only tests the reverse function in one case. Of course, I can do better than that. So let's imagine how we test the reverse function with QuickCheck. So I'm happy to see most people have used QuickCheck or something like it. But here's, for those who haven't, perhaps, here's a quick QuickCheck 101. How do I test reverse? I write a property. And the property is just a function. I'm going to be using the Haskell for my examples, but any property-based testing tool will work similarly. So this function takes an argument, a list of ints, and this type tells QuickCheck to generate random lists of integers for testing with. So that means that in my test, I'm going to call reverse on a random argument. I'm going to be able to test it in thousands of different cases. But there's a little bit of a problem, isn't there? What should I put here, where the question marks are? Because in the unit test, I knew what case I was running, and I could figure out what the return value should be, so I could check I get the correct result. But in this property, the argument to reverse might be literally anything. So it's a bit harder. I can't, once and for all, predict the result there. OK, so here's what I can do. I can just write a function to predict the result of reverse. Yeah? Is that good? The problem is, this is not easier to write than the reverse function itself. In fact, it is the reverse function itself. So now I'm having to repeat the work in my test that I did to develop the reverse function. And that is bad. It's not only a waste of effort, but also, if I made a mistake programming the reverse function, what are the chances that I make the same mistake when I program the prediction? Very high, right? And so this is a trap that it's easy to fall into when you use QuickCheck. And you end up replicating the code in the tests. And that's bad, firstly, because it's expensive. You know, what, you end up writing the same code twice. And secondly, because it's of low value. You're probably going to repeat the same misconceptions, and you won't find your bugs. So what are you going to do with a method that is expensive and low value? Reject it, right? And I've seen many people become discouraged about using property-based testing because they fall into this trap. So what can we do instead? Well, instead of trying to predict the result of reverse, I can just write a property of the result of reverse, like this one, that says that, you know, if you take any list x's, here's a list of 5 fingers, and you reverse them, and then you reverse them again, you get back the list you started off with. So that's great. That's a very simple property. It's easy to define, and now I can pass this property to QuickCheck, and QuickCheck will generate, by default, 100 random tests. And I can go on. I can generate thousands of random tests. That's great. I have great testing now, right? Or do I? Here is a particularly dumb way that I might have defined the reverse function. You might think nobody would be so dumb. But just imagine, maybe I was writing reverse and I thought, oh, I can't be bothered to write the code now. Let me just make the type checker happy. This definition does that, and I mean to come back to it later. But what do you know? it passes my tests. Right? Because if you call this function twice, you get back the same thing that you started off with. So my property that I was so proud of does not catch this stupid bug. But if I run the original unit test, of course it catches it. Here I'm just using QuickCheck to run the original test, and it's going to complain that 1, 2, 3, that's the original list, is not equal to 3, 2, 1, the result of reversing it. So apparently, the original unit test that I criticized for only testing one case can catch this error, and my property that tests thousands of cases cannot. That's not very good. Of course, I can write a property that will distinguish between the correct function and this stupid bug. Here it is. This property says reverse is the stupid one. And this property would pass for the buggy definition. In reality, my definition of reverse is correct, and so it fails. And that lets me just show you what happens when a property fails. QuickCheck prints out the counterexample, the random input. So x is a 0, 1. In that case, this property fails. And then this line comes from the assert equals. So it says 1, 0, that's the result of the reverse, is not equal to 0, 1, the list I started off with. And the cool thing about QuickCheck is that almost always, this 0, 1, this is the example that we get. That doesn't look like a random list, does it? No, it isn't a random list. This is the result of QuickCheck simplifying the failing test as far as possible, which we call shrinking. And almost always, QuickCheck will report the problem in this property with the list 0, 1. Occasionally, it chooses 1, 0. But usually it's 0, 1. And why is that? Because QuickCheck has shrunk the test case as much as possible. That has involved removing elements that aren't needed to make the test fail, and also reducing integer values. So if you think about it, to make this test fail, you have to have a list with at least 2 elements. A list with 1 element is its own reversal, or a list with 0 elements. And what's more, they have to be different. Right? Reversing 0, 0 does give you back the list you started off with, so this property would pass. So the smallest list with at least 2 elements which are different is the list containing 0 and 1. That's why we always get this example. And shrinking is one of the things I think that makes QuickCheck useful, because we end up with failing cases that are as simple as possible, where everything in the test case is relevant to the failure. OK, so that's a quick run-through of property-based testing. We've seen the really great things about it, that by using random generation, we can run lots and lots and lots, thousands of different test cases. And secondly, that shrinking ends up giving us failing tests that are minimal, and as a result, really easy to debug. But we have also seen the trap that lurks in property-based testing, that it is quite tempting to replicate the code in the tests. And if you do that, you'll pay a high price and you'll get low value. So what this talk is about is avoiding that trap. I'm going to talk about systematic ways of formulating properties, ways of thinking about your problem that can help you write properties that do not replicate the code, but are effective at revealing faults. And if I have enough time, I'm going to show you 5 different ways of thinking about your properties. I'm going to need an example. The example that I'm going to use is a simple data structure. So it's just binary search trees. Here's a definition of binary search trees in Haskell. A binary search tree is either a leaf, or it's a branch node containing a left subtree, a key, a value, and a right subtree. So these are representing finite maps from keys to values. What operations will I test? Well, I've got a find operation. You give it a key and a tree, and if there's a corresponding key in the tree, it'll give you the corresponding value. I've got 4 operations for building trees. Nil builds an empty tree. Insert inserts a key and value into a tree. Delete removes a key from a tree. And just to make it interesting, let's have union as well on binary search trees. And I'm also going to use a couple of other functions in my properties, which I'm not really concerned to test, but I just need them for testing. ToList is going to take a tree and just return the list of keys and values in that tree. And keys will just return the list of keys. So you'll see those things popping up. Now, before I can write any properties of trees, I have to be able to generate random trees. Generating test data is a whole topic in its own right, so I'm just going to pick something simple and stick with it for this talk. Here's my generator. If you don't read Haskell, I think I can explain it to you. What I'm doing is just picking an arbitrary list of keys and values, a random list of keys and values, and then I'm inserting them into the empty tree. Okay, so you can see I ought to be able to generate a lot of random trees by doing that. And before I can start testing, I also need to define how to shrink this data, and I'm just going to use a generic shrink function that Haskell QuickCheck provides. Okay, so here's our starting point. What's the first thing to think about when you want to test code like this? The first and easiest question to ask yourself is there an invariant? If so, of course we should test it. And I said that these are binary search trees, right? So, you know, we remember data structure classes some years ago. There should be an invariant that they satisfy. Let me just write a function to check that invariant. Here it is. A leaf tree is always valid. A branch tree is valid if the left subtree is valid and the right subtree is valid. And all the keys in the left subtree are strictly less than the key in the root. And all the keys in the right subtree are strictly greater than the key in the root. Make sense? This is obviously correct, isn't it? You agree? Oh, I see you were a little doubtful. So you might think that this is not the most efficient way to check the invariant. And you would be right. This is quadratic in the worst case. But actually, I don't care about that. When I write this kind of function that's going to appear in tests, I optimize for obvious correctness. So I could write a more efficient function, but I might make a mistake. And then, if there's a bug in my tests, then understanding the results will be difficult. So this is a piece of important advice, I think, to keep these functions as obviously correct as possible. So now I can just write a whole lot of properties, right? For all the functions that build a tree, well, nil is one of them, then insert, delete, and union, the result should be a valid tree. Very straightforward. You'll notice that each property has two lines here. There's the actual definition, and there's the type signature, which I've written in gray. Those type signatures are needed, along with some type definitions, to tell QuickCheck what kind of data I want to use for tests. So I've written the gray bits to specify that I want to test using integers as keys and integers as values. They're perfectly good as test data, so why not? You have to write the gray stuff in practice, but because it's not my main point today, I'm going to elide the type signatures in the rest of the talk. But just imagine them. They do need to be there. OK, so now I've got 4 properties. So, of course, if I were to plant a bug in any of those functions, the corresponding property should fail, right? And so I should be able to quickly see which function is at fault. Let's try that. Let me plant a bug in the insert function. OK, I'll run my tests. What happens? They all fail. What? But I would put a bug in insert. Why did these other properties fail? Well, if you look at them, you can see QuickCheck shows us on what arguments delete and union fails. And if you look at this input to to delete, you can see it's got a key 1 to the left of a key 0. The input is invalid. So of course, delete returned an invalid output. Same thing happens for union. I've got 2 occurrences of the key 0. That's not allowed. So the problem is that what the properties actually say is that no matter what junk you give these functions, delete and union, they will somehow magically return a valid tree. And of course, we don't really mean that. Of course, we only want to test them on valid inputs. So what's happened here? I put the bug in insert, right? Do you remember how I generated test data? I used insert. So my generator is generating invalid trees and supplying them to other functions under test. When this happens, it is very, very confusing. So whenever you write tests, one of the things you have to do is test your tests. Here's a property that I must also write. What does this say? It looks as though it's saying all trees must be valid. What's it testing then? What it's testing is the generator. It's testing that every tree I generate is valid. And so it makes sense to carry out further tests using them. So I always write and test this property. And if this property fails, there's no point looking at the other ones. So it's an important first step. OK, so now if I remove the bug in insert, then this property will pass. Of course, I also need to test that the shrink function constructs valid test cases. And I can do that like this. The shrink function returns a list of smaller examples. And so this property just says, every tree I can obtain by shrinking t is also valid. Unfortunately, that fails. Why does it fail? Well, it fails because one of the things that this tree can shrink to is this one. And if you look at that second line, the key 0 appears twice. So that's invalid. But unfortunately, if you look at the first line that was t in my test, that is also invalid. What is going on? I told you, I fixed insert. I tested that first property. I know I'm only testing with valid data. But here, QuickCheck reports a failure with an invalid tree being shrunk. Do I care that invalid trees might shrink to invalid trees? Of course not. What I want to see is, can a valid tree shrink to an invalid tree? Any idea why this happens? It's because there's a bug in shrink, of course. But before QuickCheck shows me this counterexample, it shrinks the test case with an invalid shrink function. And you end up seeing something that's not useful. What's the fix? Just to adjust the property. So this adds a precondition to the property, and it kind of hardens it against invalid test cases. Now the property says, if t is valid, then all the shrunk versions of t will also be valid. And so QuickCheck will then, it may generate test cases that don't satisfy the precondition, but it doesn't run them. It just discards them. So all the tests that are run will now satisfy that precondition. And now QuickCheck reports the right case. Shrinking can take a tree containing keys 0 and 1 and shrink it to a tree containing keys 0 and 0. Why is that? Because I just used a generic shrinking function from QuickCheck. And the generic function doesn't know anything about the invariant that my data structure is supposed to satisfy. And so, of course, this also introduces invalid shrinks. It's easy to fix. I can just throw in a filter to discard the invalid shrinking candidates. And that then will make everything work. OK, so that's testing invariance. That's very useful. Second idea, ask yourself, what is the postcondition of each operation? OK, this is rather vague advice, I know. It's like saying, think of the postcondition. It's a bit like saying, think of a property. But it is helpful to ask yourself, what should be true after calling a function? So what should be true after calling insert? Well, we should be able to find the key that we just inserted, right? And if we try to find any other key, it should be the same as it was before the insertion. So I can write this as a property. Okay, so for any key, value, tree, and other key, if I insert k and v into t, and then I find k prime, what will I get? Well, it depends on whether or not k and k prime are equal. If they are equal, I should get just the value that I just inserted. Otherwise, I should get the result of calling find on the tree before the insertion. Okay, and this is a very useful property to write. There we are, and that, I was going to go through it. The one thing you might wonder is, how often will these two keys be equal? Because they're chosen independently. And the answer is occasionally, maybe about 5% of the time. So a lot of our tests here are going to be testing that insert didn't corrupt any other keys in the tree. It's important to test that. But you might question whether the balance of effort here is really appropriate. Anyway, let's not worry about that. Let's think about more postconditions. What about find? What's the postcondition of find? Well, when we call find, if the key is in the tree, then we should get just the value. If it's not in the tree, we should get nothing. So I've got two cases in the postcondition. So given a test case, I need to decide, I need a function really that tells me, was the key in the tree? And if so, what was the value? If only I had that function, I could write my postcondition. But wait a minute. That is the find function. I have just stepped into the trap. So I'm stuck. It looks as though I need find to test find. What can I do instead? Well, a very useful idea is instead of writing a test that checks to see which case we're in, let's write a test that guarantees that we're in one case or the other. So I will actually write two postconditions for find, one of which I guarantee that the key is present by inserting it, and in the other one, I guarantee that the key is not present by deleting it. And now, in each of these cases, it's easy to predict what the result of k should be. So sometimes you need to be a little creative when you write postconditions to avoid stepping into the trap. There is something about this property that should make you a little bit uncomfortable. And the question is, this first property is supposed to cover every case in which the key is present in the tree. Can every tree containing k be expressed in the form insert kvt? It's not obvious. And if it's not true, then I might be testing find only in a subset of cases, and that could lead me to miss bugs. Okay. Postconditions, they're useful. Here's a third idea, metamorphic properties. So the idea behind metamorphic testing is this. Maybe it's hard to predict what the result of a function should be, a function that we want to test. Okay, let's not do that. Maybe it's going to be easier to predict how changing the input to a function will change its result. That can be much easier than predicting the actual result itself. Here's an example. If I start off with a tree, and let's suppose I want to test insertion, so that's going to produce some other tree. I certainly don't want to try and predict what tree I should get. But suppose I modify this tree before doing the insertion. What modification might I use? Well, perhaps I might insert a different key and then do the insertion on that. What's the relationship going to be between these two trees? Well, obviously, this tree should contain everything that this tree does, and it should also contain k prime, right? So that relationship should hold, and I don't have to predict exactly what tree I should get. I can just predict that, if I insert k prime into this tree, then I should end up with the same result. So this is the basic idea behind metamorphic testing. You think of an operation you want to test and a way of modifying its input. And if you've got n operations that you're working with, that gives you a quadratic number of ideas for properties, right? Because for every operation that changes the argument, you can ask, how will that change the result of every other operation? So there's a rich collection of ideas here that we can use to write properties. Now, if I just write down the property corresponding to that diagram, it looks like this, right? It says you can swap insertions over, basically. Here is the original call that I wanted to test. Here's the call with a modified argument. And this bit of the property is checking the relationship between the two. So metamorphic properties always have this kind of form. Of course, you might wonder, is the property really true? Now, you might start thinking hard about this. I don't do that. I let QuickCheck do my thinking for me. Okay, so there might be a small problem. Let's just test it and see. So if I do that, da-da, oh, it's not true. Why isn't it true? Because in this case, where we insert the same key twice, then the second insertion wins. Oh, well, okay, that's a special case that I didn't think about when I was drawing the diagram on the first slide. But it's easy to cope with, right? So I can just modify my property to treat the case when the keys are equal as a special case. And in that case, what should I get? Well, in that case, modifying the input by putting a different value for k has no effect. So I should get the same result as just doing the second insertion. OK, so now I've corrected the property to fix the bug that QuickCheck showed me. Now I can test it again. It still fails. OK, it still fails. But now in a case, here it is, where I'm inserting two different keys. But look at the results. These are the two trees that were not equal. That's what QuickCheck is complaining about. And if you look at them, you can see that this one contains key 0, value 0, and key 1, value 0. Whereas the other one contains key 0, value 0, and key 1, value 0. They contain the same keys and values, but the shape is different. Do I care about that? Well, I think not. I think this, I would not call this a bug in the code. So my property is too strong. It's checking that I get trees of exactly the same structure. And that isn't what I want to check. So very often when we write these metamorphic properties, we have to define an equivalence on trees. And I'm going to say two values are equivalent if they contain the same list of keys and values. And now I can modify my property to use this weaker check, and da-da, the test will pass. And I can go on to write many more metamorphic properties using the same ideas. Metamorphic testing, by the way, it's not something that is only useful in the context of QuickCheck. In fact, it's an entire research field in its own right. And there's a series of workshops that apply metamorphic testing in many different contexts. So it's a really, really useful idea. And this was the 4th international workshop, which was held this year in Montreal. Next year, there will be one in South Korea, I believe. So there's a lot more to dig into in this topic. OK. Now, I said we would see 5 different kinds of ideas if there was time. There isn't. So let's jump straight to the 5th. The 5th idea is what I call model-based properties. So here, the idea is, suppose we start off with some tree, and we insert something into it. It's hard to predict what the result should be. But suppose I convert both the tree before and the tree after to just the list of keys and values. Now, can you predict how these two lists of keys and values should be related? Yes, it's easy. Here we've got a much simpler data structure, and I can just reuse list insertion. Okay, so we talk about this as using an abstract model The toList function is the abstraction function. Given the real data structure, it gives me a model of the data. And then we call the arrow on the right the abstract operation. It's an abstract implementation of the real implementation. We use the abstract implementation to test the real one. Here's the property that I would write for that. So this tests insert by calling the real insert function, converting the results of the abstract list, and then taking the argument, converting that to the abstract thing, and using the list insertion function. And when I test this, what will happen? It fails, of course. Why does it fail? Well, down here, we see the output from the assert equals. On the left, what I've done is I've inserted key 1 into a tree that already contained it. And the tree insertion function, of course, discards. You don't get a duplicate key, but list insertion allows duplicates. So it turns out list insertion wasn't quite the right abstract implementation. I also need to include deleting the key if it was already present. So I have to make a small change, and now I've got a property that tests insert very effectively. What I love about this is this idea of using an abstract data structure and abstract operations. It comes from a paper by Tony Hoare in 1972, a classic paper on proving the correctness of data representations. And this is something that I personally find extremely satisfying, that I can take, proof ideas from the 70s and turn them into highly effective tests. It's great. OK, so I've shown you 4 different ways of thinking of properties. How effective are they? Well, one of the things that we can look at how many properties there are of each type. So I applied these methods consistently. I wrote 4 invariant properties. I showed them all to you. Those tested valid. I wrote 5 postconditions. That's including 2 for find. I came up with 16 metamorphic tests. Remember I said there's a quadratic number of ideas for properties. So I thought of lots of those. And I have 5 model-based tests, because there are 5 operations under test, and you need 1 each, 1 property per operation. OK, so now you can see roughly how much work there is writing properties of each sort. But how good are they at finding bugs? To find out, I planted 8 different bugs in my code. 3 bugs in insert, 2 in delete, 3 in union. And these vary from blatant to quite subtle. And then I tested 1 bug at a time to see how effective were the properties at finding them. OK, so here's the good news. Apart from the invariant properties, which missed 5 out of 8 bugs, not surprisingly, those are bugs that don't break the invariant. They just do the wrong thing. OK, so apart from those properties, which we write because they're easy to write, but we knew from the start they would not be very strong, the other kinds of properties were all able to find every bug that I planted. Now, that doesn't mean that they're all equally effective. So I wanted to measure how effective is each property of each type. Let me explain to you how I did that. Here is one of the postconditions I wrote for find. So if you just look at this property, you can see that potentially it might find a bug in find or insert, right? But here's the point. It will not find the bugs in delete and union, because it doesn't even call them. So if we think of the bugs I inserted, those 5 cannot be found by this property, obviously. The other 3 potentially might be found by it. How many does it find? It turns out that this property finds 2 of the bugs that I inserted, but the 3rd one cannot be found. It doesn't violate this postcondition, even though it does introduce a bug. So I'm going to say that the effectiveness of this property is it finds 2 out of 3 possible bugs. And I did that for all of the properties I wrote. And here are the results. For the invariant properties, we know that they missed 5 bugs altogether. So if you sum up these effectiveness scores, they're about 38% effective. The postconditions, if you test all the postconditions, they find every bug, but each property individually, on average, only finds about 80% of the bugs that it could find. The metamorphic properties are better. Each property found 90%. And the model-based properties were the best. They found 100% of the bugs that they could potentially find. So the model-based properties are complete tests. So this gives us a pretty good idea that model-based properties are the best, metamorphic one's next best, and then postcondition's not quite as good as that. It's also worth asking, how quickly do the properties find the bugs? And I measured that too. This is just for one bug in union. And you can see up there at the top, the red box, that's the postcondition. That finds this bug, on average, after 50 tests. The yellow box, that contains a number of metamorphic properties. And the number of tests you need to find the bug varies. Down at the bottom, we have the model-based test. On average, that finds the bug after 8.3 tests. 5 times faster than the postcondition at the top. Even though, if you read them logically, the postcondition at the top and the model-based test are equivalent. So, this is also something to bear in mind. Why this huge difference in performance? Here are the two properties, the postcondition at the top, the model-based one at the bottom. The postcondition, look at the arguments. The test takes as inputs 2 trees, t and t prime, and a randomly chosen key. The second property just takes those 2 trees. So if you choose 2 trees that provoke the bug in union, to find the bug with the first property, you still have to have been lucky in that you chose a key for which the result is wrong. The first property tests 1 randomly chosen key. The second property, because it uses the model, checks all keys. And that's why the second property finds bugs in many fewer tests. I actually measured mean time to failure across all of my properties and 7 of my 8 bugs. And as you can see, the postconditions, on average, they needed almost 70 tests. The metamorphic properties, about 60. The model-based tests, around 6. So the model-based tests were very, very much more effective. So what's the take-home message? Well, model-based tests, they're great. They're much easier to think of than postconditions because you can do it systematically. You come up with this abstract representation, and then you just work with that. You only have to write 1 property per operation. Many fewer properties than if you write metamorphic tests. They're the most effective at finding bugs and the fastest at finding bugs. And this is partly because the model-based tests form a complete specification, which is nice. So then you might say, why ever would you use anything else? The problem with model-based tests is that you need the model. And in some situations, the model ends up resembling the implementation. And then the trap is waiting there for you to put your foot into it. It's good to have a second string to your bow, and the best second string is the metamorphic tests. The great thing about metamorphic tests is they do not require a model. They are the easiest to come up with. I showed you that method, the quadratic number of ideas. You just have to think, OK, if I change the input before calling this function, how do I expect the output to change? And they're not quite as effective as model-based tests, but they're not far short. So that's the other string to the bow. And I think I'm out of time. So, by the way, there is a paper about this. I tweeted the link quite a long time ago, but since I almost never tweet, if you search for @RJMH in a relatively recent tweet, you'll find a link to the paper, and it's not behind a paywall or anything. You can just click on it, and there's more where this stuff came from. Thank you.
All right. Quick questions? Hi, John. That was great fun. Thank you. You were measuring effectiveness of testing in terms of the number of test cases, and the postcondition test for union took many more test cases than the model-based test for union, because model-based test was testing all keys, not just one key. Of course, that's a bigger test. It's testing all keys, not just one key. So presumably, if you take the number of tests and the amount of time the tests take to run, if you care about that, they're more comparable?
Yes. So if you measure the time taken to find a bug, then the difference will be smaller. They won't be comparable, because even for the postcondition test, we have to generate the entire tree. Right? So you're already paying a down payment generating all of this data. So needing to traverse it in the check, it's, you know, it might slow you down by a factor of 2 perhaps, but it's not going to be more than that.
Any more questions?
So the examples you're giving, I think, illustrates one problem I have with property-based testing, that, as you said, you have the model almost for free with this, but also most of these examples are on pure functions, and most of the tests you would want to, or things you want to test, are kind of stateful systems, which are almost requires you to model. Yeah, I noticed that. What do I? So a lot of the code I want to test is not pure, and maybe as a good Haskell programmer would say that it's kind of one of the benefits of Haskell is that you can have all the pure stuff is going to mostly work, and where I have my boxes in the impure stuff. So how can I test that part?
Oh, you can write lots of bugs in the pure stuff too.
Sure.
Yes, of course you're right. So I've chosen pure functions to talk about here and to write about in the paper. It's a simple case, and you know, I think there's plenty of intellectual material just in talking about testing pure functions. Of course, a lot of testing that one does in practice is of the stateful code, but actually, many of the ideas they transfer over, like postconditions. That's one standard way of testing stateful code. The model-based idea, that is actually the way that at Quviq we develop tests for stateful code. Now, the metamorphic testing, other people have applied that to stateful code. That workshop series I referred to has lots of papers about that topic. And I would like to find a systematic way of incorporating metamorphic testing as well, because that also works for stateful code into a property-based testing library. That is future work. But the ideas here, they are applicable to testing stateful code too, except that you also need a whole mechanism on top of that to make the stateful testing possible. Subject of another talk.
All right, thank you very much, John.